Great. So thanks for joining and staying with us. So I'm Roberto Mari. I'm part of the Barefoot product management team. And I'm responsible for some of the applications and things you can do on Barefoot thanks to the programmability. And with me, I have Chang. Chang, you want to introduce yourself briefly?
I'm CTO of Applications at Barefoot Networks.
Great. So today we'll talk about a little bit, click through more details around telemetry. So we heard the entity use case, right? That was great. The ability to check and monitor latency they have on the smart edge gateways. We heard the Netcope and Intel guys talking about the Intel use case and NT use case there. And so that's the agenda. It's pretty aggressive. We'll try to get questions at the end and try to save time for talk and going through slides and material. So before we start, I have a quick commercial break. And we are announcing here at ONF Connect our next gen Tofino platform. So this is called Tofino 2. Is a new chip we have, a 12.8 terabit chip. It's unique in a way. It's a 7 nanometer technology chip with 50 gig of SerDes, so a lot of ports supporting 400 gig, better power footprint. And we have a modular chiplet architecture. So we disaggregate the die for the pipeline and the processing engine from the SerDes and interconnecting to the I/O. It's still based on of course, PIS architecture. So any P4 program that you guys are running today on Tofino will be very, very easy to migrate on the Tofino 2. And basically, all your program will fit. This chip will also have more memory and more capabilities. So, it's an easy transition. So with that, let's go back to our presentation and a quick highlight on the benefits of a programmable P4 switch. I don't have to spend a lot of time here. I mean, you guys know that, it helps a lot with use cases. Contrary to what people think, people don't use much P4 to add lots of features. They, in fact, use P4 to more remove features and just focus on the requirements they need. So it helps stripping out complexity. Of course, helps future-proofing your data center. So you should migrate to that next generation chip only if you need more speed and feeds and you need more or additional capacity. But the idea with the programmable platform is that you can deliver a new feature at the speed of software. So that also helps with scale. Of course, the moment you can focus your resources on the set of features you need, you can really scale it out and implement the functionality you want. And last, we have great telemetry capability on the chip. So we're going to talk a bit about what people are doing with telemetry and INT and talk about what are the unique things that this technology enables. So before I jump on the telemetry, of course, with any solution, you need ecosystem. And we have a very broad ecosystem of platforms there. They are based on the Tofino ASICs. So today we have, of course, our Tofino 1. And in future, we will have platforms based on the Tofino 2. We have a number of white box vendors, a number of network operating systems that you can run in the disaggregated model. So you go from, of course, Stratum to ONL, IP Infusion, and Sonic. So let's go and talk about the telemetry, why we think it's unique. So with this telemetry solution, you can track every flow with this flow reporting capability. So the ability to monitor every flow and every path to measure latency and issues, it's a capability of INT, of inbound network telemetry. We also have lots of other capabilities. And one more functionality that the data plane telemetry can offer is the ability to report on packet drops. And when I say reporting on packet drops, I just don't mean like, hey, there was a packet drop, but offering metadata on why that packet was dropped, on which switch, what was the reason, which flow that packet belonged to, associate timestamps. So give all the information you need to really root cause the problem, and build rich analytics on top of it. And then be able to track every congestion. So this is the ability of INT and data plane telemetry to generate and track congestion events. We can produce with Barefoot also packet level snapshot of a congested queue and generate what are called queue reports. So you're looking at INT as one of the methods, and then you're looking at drop reports and congestion reports as additional metrics, additional telemetry that the platform can offer. So what is INT? And at the very high level, with INT, you have this concept of an INT domain. So the first INT-capable device in that domain will instrument packet for specific telemetry, and that instrumentation is really function of the use case. We hear from customers about different use cases there, and this is just an example. We're adding switch ID, we're adding timestamp, we're adding queue delay, because we want to track the path and the latency of that packet across the network. And as that packet goes, more metadata is added up to a termination point, which we call the INT sync, that will extract the metadata and send the metadata out to an analytic engine for analysis, for ingestion, and for analytics. So as you can see in this environment, not all the switches are blue. So you may have switches or hopes or devices in the pad that are not INT capable, and that's fine, because this technology can also work very well in a brownfield environment where not every device is INT. So what makes that telemetry important and something that people are really looking at? So first of all, it needs to be flexible, adapt to the design of the customer. So that's why alongside with INT that instruments telemetry and metadata into packets, you also have additional methods such as postcards. With Postcard, every device capable of streaming telemetry will generate telemetry information without adding any overhead or information into packets. And this really, I put some highlights down there on what are the use cases where this is more required. For example, if you have a single switch or a single opening network, INT doesn't really make sense in that case, because if you have a gateway kind of use case, you want to monitor what's happening on the gateway, and that's it. So brownfield or environment where you have a single device, that's where you will use the postcard mode. The functionality-wise, that method is completely equivalent to inbound network telemetry. So the same type of visibility you get with INT, you can also get with postcards. And with postcards, you can say, for example, hey, I've seen the packet, I forwarded this packet on this interface. So it's up to the analytic engine on the other side to correlate and reconstruct the path and the latency, of course. Also, this technology doesn't have any dependency on encapsulations or marking the packets, just to make sure that's an INT packet. I think there was a question about what encapsulation you guys use for INT, right? If you don't want to get in that business of having special encapsulation, or this is probably a better approach. And of course, you have the traditional INT method. It's a little bit easier for greenfield, and of course, is more efficient, because now in INT, that correlation of what happened to that packet when it goes through the network is built into the packet. Is the metadata that you collect, and you generate a report on the sync device. So it's more efficient also, because instead of having every op generating telemetry, you have just a sync device that generates that telemetry report. So as I said before, additional type of telemetry information we generate on top of INT and postcards for flow tracking are the drop reports and the congestion reports. And these are extremely important, because if you want to track the performance characteristic of a network or find application issues, you need to correlate the flow information with what's happening on that specific device in terms of congestions, in terms of drops. Specifically with congestion reports, not only we can detect and report a congestion such as a microburst, but we can also tell that endpoint analytic engine, hey, this flow was sharing, these reports tells me that this application was sharing the queues with other applications. So other flows were present in that queue. And this is an information that you can reconstruct thanks to the fine-grained information you get from every switch. So when we look at INT, I think we were probably one of the first vendors that brought it to market with use cases and so we had a lot of trials and investigation with customers, discussion, and we came up with what we call the characteristic that the INT solution needs to have in order to be production ready, right? And we'll cover a little bit about that, but this solution today runs in production data centers at some of the largest hyperscale. So it has to be proven, of course. It has to be engineered in a way that is not only flexible, but also scalable and something that people can practically deploy. So what is the characteristic that such a solution should have to be production ready? It has to be smart. So you want to have the ability to tell what specific application you want to instrument or observe. And we have a concept of a watch list. So it's fundamentally an ACL-like matching rule that tells, hey, I want to instrument just these applications. I want to just observe these applications. I don't care about anything else. Also, you need to be flexible and you need to have the ability to tell what information you want to collect. That will fundamentally define the use case of the visibility, of why you're introducing the telemetry. It could be because of, you want to track the packet latency. Think about NFV use cases where you want to track where the packet goes in the service chain, or track congestion events. Think about when you have, Hadoop applications or Cassandra that can generate in-cache congestion issues. Also, what's very important in that smart is be able to generate reports on a trigger base. So we have the ability to observe every packet. That's great. But you don't want to generate reports on every packet because in this type of networks, you may have billions of packets per second. So that trigger technology allows you to generate reports only when the data plane observes a specific problem or issue. So that gives that right deduplication functionality to make any analytic solution be able to scale and ingest the data. Of course, it has to be programmable. So everything that we produce as a P4 implementation. Specifically for INT, we have open source a P4 implementation. And thanks to the portability of P4, we have now not just switches, but smart NICs, thinking about Netcope that we just saw before, and other smart NIC vendors that are implementing these INT technologies on their platform. We're also talking with other type of solutions, like when you have virtualization. Sometimes you want to get this into OVS because you want to track where that packet has been or where that packet goes when it goes to a container or a virtualized application. And last but not least is real-time characteristics. So that's another very important characteristic of this. You want to have real-time characteristic to generate reports when the problem occurs because you want to react to the problem very, very fast. So this is kind of a comparison of what that solution offers in terms of unique capabilities. And if you look at Tofino and our advanced telemetry in combination with Deep Insight, there are a number of differentiating features. The ability to push information directly from the data plane rather than involving the CPU. The ability to monitor every packet. The moment you actually sample a flow, to monitor that flow, or the moment you mirror and capture and replicate the packet or truncate the packet and you instrument that packet, you are observing something different that fundamentally can lead to the wrong conclusion. So be able to instrument and observe the packet is very, very important. The ability to have hop-by-hop telemetry, that's another important characteristic. If you can deploy INT in your network for different reasons, having postcards or having op-by-op telemetry, of course, with drop reports and queue reports, is very important to kind of give the right set of visibility. We make any of this. So on the coverage side, and I have highlighted in red some of the more important things, we can, of course, observe every packet, and we can make the traffic reports very relevant, because now what you observe and what you get a report on is only because of a change in the network or because of an anomaly. So the information that you get as streaming telemetry, it's only the problems, it's only the changes, it's only what goes beyond the specific baseline that gets monitored. And of course, the programmability is another aspect. Thanks to P4, we can adapt this solution to different kind of use cases. So a quick discussion about Deep Insight. So of course, with all this telemetry, the first problem we had is how we visualize this telemetry, how we generate analytics out of it, and how we visualize these analytics. And so we came up with this Deep Insight solution. Deep Insight is a software-based solution that runs on commodity servers. And you have two interfaces, a southbound interface to these programmable data planes that can generate streaming telemetry. So it will ingest INT reports, drop reports, queue reports, and a northbound interface that feeds now this data into third-party network management solution. So Deep Insight has a full UI. It can visualize all the analytics and the telemetry data. But you also have a northbound API. So if you want to integrate this in Splunk into your networking system, management system, or in ServiceNow, for example, if you want to generate a ticket on a specific anomaly, that northbound interface will be used for that. Some of the key features here, not spending lots of time here, but the ability to visualize pattern latency, the ability to detect congestions, the ability to detect and do packet drop analysis thanks to all the metadata that gets associated with it, and the ability also to correlate all these issues back to the topology and visualize things in a UI. We also have data retention in the system that allows you to go back. Imagine like you have a TiVo and you want to go back and find out what were the issues like last week or in the last 2 days or so on. And thanks to the fact that now the data plane telemetry is very efficient, thanks to the trigger-based telemetry, thanks to the deduplication that you get through these programmable data planes, we can scale very well. This is the first big data solution that can be deployed on a single server, which is kind of big if you think about it. So kind of a summary, and this product is also showcased at our booth, so if you guys want to stop by and take a look. I want to touch base also on work that we did with ONF and the Netcope guys. So this solution can be deployed to monitor type of telco networks where we do service gateway offload and monitor for latency and monitor for path in this solution. That same INT technology is used on the leaf and spine, running the Stratum OS, and on the Netcope NIC, running their own P4 program for INT. Now with that, we want to show you a quick demo and see, so you guys can see live what is this.
So yeah, we wanted to come up with a very realistic network debugging scenario that a lot of network admins can bump into. So let's just start. The test topology, typical leaf spine topology, and then you have 3 servers and 2 leaf, 2 spine, 25G NICs to the server, and then 2 by 10G at the between the switches. So you have, say, under leaf 1 you have 50G, and then under leaf 2 you have only 25G. You have up to 40G in total, slightly oversubscribed. On the other leaf, it's not even oversubscribed. Obviously, we're using lag and ECMP together here. Okay, this is the network. And the first test, let's start with some iPerf sessions from client VM1 to VM2 with some 20 number of TCP connections. Okay, so VM1 starting iPerf to VM, the other receiver VM. We just started that, and about 20 connections are created. And we're looking at DI. DI is, the deep inside is immediately discovering the new flows. 40 flows are immediately discovered. And then this is the, by the way, the time range that we're looking at. We're using real-time monitoring mode. So this entire vertical screen covers last 30 seconds of the events and anomalies that are discovered. Okay, so these are all, expected events. No anomalies discovered. And if you look at the server side, I was expecting 25G, but it's only about 8G. So what's going on? Something is wrong here, okay? So, okay, maybe I didn't create enough number of connections, so let's start with 40 connections now. Okay, I started 40. Well, roughly the same throughput, okay? I have 2 servers, client server, 25G NICs, enough network bandwidth, what's going on? Still no anomaly. A lot of just new flows, but no anomalies. Okay. Now let's look at the big sort of deep down features. Okay. So in this view, sorry, let me just go back a little bit. Okay. So the switch topology view. Now, here, in this view, you can actually observe the switch hop level latency in the unit of nanoseconds, and because our monitoring window is 30 seconds. This actually shows the maximum latency observed in that switch last 30 seconds, okay? So obviously, yeah, a little bit of latency increase happened on all these switches because if you didn't have any congestion, our switches hop latency is sub-microsecond, a few hundred nanoseconds. Now you can see that the latency is up to a few seconds, but on this particular switch, the maximum latency happened to be some tens of microseconds. So that's not that terrible, but it's noticeable, right? So let's see what's going on. Okay, so you can click this switch, and then there is no anomaly, but the latency was a little high. And then if you look at the other switch, again, there is no anomaly, no drops or something, but the latency is a little high. So the congestion is obviously happening here, but not that significantly. Okay? And if you look at the individual flows that are going through this, you can observe that occasionally the latency is a little higher at one of the switches. This purple switch is the leaf 1. And then that's 19 nanosecond at this point, and then it comes back down to a few microsecond. So, but the conclusion is that there's nothing that is terribly wrong in the network. There's no packet drops, significant packet drops, but still, I cannot achieve 25G. Okay, so what's going on? Could this be an end-host networking problem? Some bottleneck that is happening within the server or client? To confirm that, I started the second test, okay? Another sender, and then I created another receiver VM within the same server. Okay. So the same set of connections, 1 pair, and then I'm starting the second pair now from a new physical machine to the same physical machine, but the second VM. And then I started that. And then if you look at the achieved throughput, now I achieve more, okay? So I achieved roughly 2x throughput. And so indeed, there was some bottleneck on the receiver physical machine, especially hypervisor layer that performs some resource allocation at the VM level. So by increasing or adding another receiver VM, I was able to increase the total throughput. But still, the total throughput is less than 25G. Okay? It's about maybe 15, 16 Gbps. So I didn't actually solve this entire problem yet. So what's going on? So I decide to look at the DI, deep inside UI. Now I see actually some problems here, right? It's not entirely idle. I see some packet drops here, and then this says it's drop traffic manager, so it's tail drop. I also see some congestion events up there, and then end-to-end latency changes and hop latency change events are happening a lot more frequently. So I can click one of these, and then I can confirm that the drops are happening mainly at one switch. And then I can also confirm that the congestion is affecting a lot of flows here. Okay. Good. Now let's go to the topology. Okay. So LEAP2 has now significantly higher latency, some hundreds of microseconds. So let's look into that. Then it confirms that LEAP2 is actually now leaking traffic. It is introducing tail drops. LEAP1 has high latency, but it has just high latency, but it didn't drop packets. Okay. So why does this network problem occur under such a low network traffic workload? It's carrying only about 15G, 16G, and the reason is that we're looking at microbursts here, right? So as you can see, these are 25G NICs and then 10G NICs. And although you may think that there is only, say, 15G of traffic that you need to carry from here to there, that's only sort of larger scale view. If you look at multiple RTTs time scale, say a few milliseconds, yes, you're receiving 15G traffic. But if you're looking at sub RTT level, say a few tens of microseconds, hundreds of microseconds, it's actually 50G because 25G flows arriving at 25G can try to go out to one of the 10G ports. So you have this speed mismatch-based micro-congestion happening right now. That's why you can observe this kind of latency increase. And then the same kind of problem happens on the other side. Although there is no mismatch, this is actually 10G to 25G. Now, the problem on LEAP2 is that four input ports are trying to compete against only one output. And then that, again, sub-RTT level, it's 40G because there's 4 10G links going out to 25G. Okay? Because of that, even if you have relatively low traffic volume, you actually can observe microbursts. And then this is the real problem that kills a lot of latency-sensitive applications. Okay. So, so to confirm that even further, I ran the final test. No, here I actually killed one of the links here. I used to have 2 10Gs. Now I have only 1 10G. Okay, let's see what happens. So I'm killing that link on LEAP1. Okay, so soon deep inside we'll discover the path change events because I killed one port. Some flows are now remapped to a new physical path. That happened, and then as you can see, the intensity or the amount of anomalies that we receive has increased significantly. Okay, and if you look at the switches, individual switches, now you can see that LEAP1 has even more latency. And if you click that, now LEAP1 starts to drop packets. Okay. Great. So the congestion got moved over from LEAP2 to LEAP1 because LEAP1 has only now 30G of links. Okay. 50G to 30, or one of the 3 10Gs. Okay, that's what is happening. So let me conclude the demo with this, and let's go to the slide. Sorry, how can I go back to the slide mode?
Yep.
Okay. Okay. So just to conclude the data plane telemetry package that we have on Barefoot solution, it's real. I mean, you just saw that it's actually working at full line rate. It's proven because it's actually not in our test bed. It is actually adopted by some of the large online service providers in US and China and other countries. And the P4 implementation, part of this is already actually open source. We intend to open source the rest soon. And then it's extremely accurate, right? The demo is actually live at the booth. You can observe, you can see this live. So please feel free to stop by today or tomorrow. We're using some of the OEM, brand name switches and white box switches to run this demo. And then there are more information that you can acquire if you follow these links about the open source and so on. So thank you very much. If you have any questions.
Thank you.